it's another way of seeing it, and it's loose. So if I try to take the magnet away, the thing wants to stay inside. It doesn't want to leave. Well, it's not so much it doesn't want to leave. When I try and take the flux away, it induces an EMF, which induces a current in the aluminum, because it's a conductor, which tries to oppose the change. And if you step through all that, it can be complicated. You'll see that it produces an attractive response between the pendulum and the magnet. So it's being attracted, it's being held in there. But once I get it out and I try and put it in, it repels, right? If I try to put it in there, it's going to repel. And so that's the negative sign. It's always opposing the change. What's sometimes helpful, because this can be confusing, and when you do the assignment, you'll see you'll get confused sometimes, is if you're not sure about this, check it against the idea that maintain the original. Right? It's the same thing. If you're opposing change, you're trying to keep things the way they are. And so how is it? It's inside. What's going to happen if I try to get it outside? It tends to stay inside. What happens if it's outside? It wants to stay outside. It's going to try and prevent its, the response is to try and prevent it from going in. And so when you do these problems, you have to see it over time. You have to see it like a movie. So if there's a loop of wire and I'm going to stick a magnet in there, first of all, I have to know which pole. So let's take the south pole. If I'm putting a south pole in, how do I want to draw the picture? Well, the field lines are going into the south pole. But it starts at 0, right? So as I move the south pole in, and I'm watching the video, I see, okay, I see increasing vectors this way, because they go in to the south pole. So they're coming out into the magnet. And when it's here, none of those field lines are in. It's too far away. So as I move it in, I'm getting this. So it wants to maintain the original. It wants to keep it 0. So how do you deal with that? You induce a current that produces a field that cancels the increase. How do you produce, if the current has to give you this to oppose the change, then write in rule number 3, the current has to be this way. So if the current is this way, okay, well, you get to do it. I said, you don't look happy. You don't this way. You got to sit down and do it. Watch me do it. What? Okay, I'll say it one more time.
It's like the current cancels.
Well, you're watching the movie. What do you see? You see the dots increasing. How do you prevent that from happening? You got to cancel them out. You got to. If you see a dot, you do an X and it goes away.
What are the dots?
The dots are vectors coming at you.
Oh,
And why are they coming? They're not really coming at you. They're coming at the magnet. And why are they coming at the magnet? Because I said this is the south pole. Oh, you got to know though that the field lines go into the south pole. Why did I do that? Because I usually do the north pole. If you're looking at the north pole, what do you see? You see points coming at you. But when I turn it this way, the points going into the board, you're seeing the vectors go away. You're seeing that. So if these are increasing, then you get a current that way. How come it's opposite? Well, because I changed the magnet around. Now I'm not getting dots, I'm getting X's. And the other way, if this is still like, oh, I'm getting it wrong, think about it this way. It's more physically intuitive even to me. If I'm going to put a North Pole in there, what's that, what's the magnet going to run into? It's going to be repelled, right? When I go in, it's not going to pull it out of my hand. It's going to oppose me. I'm going to have to push it in. How do I know that? Because I know I have to do work to crank the generator. So if this is a North Pole, the current is going to be such that that's a North Pole, like the coins. And so the current goes that way. What are you doing? I'm doing right-hand rule number 3. If I want this to be a North Pole, right-hand rule number 3, the thumb is the North Pole. That's the South Pole. I have to get that. And that tells me the current's going to be this way. Okay, now the magnet's there. The North Pole is there. The field lines are going into the board. Now try and remove it. So you can do, okay, you're removing the field lines, you're going to try and replace them. That's a current in the opposite direction. Or if I'm pulling the North Pole out, this will become a South Pole, right? It'll attract it, just like this. If I try to pull it out, it's attractive. So that becomes a South Pole as I try to pull it out. It's a current the opposite way. So anyway, you have all those tricks. Different ones may work better for each of you. And you got to practice and come up with your best method of applying Lenz's law and figuring the direction of things. Here, I have another one that we can practice on. You'll see in the assignment. Remember I said we have this, and we can vary this by changing BA cosine theta. And yesterday we changed the B a lot, and we didn't change A. So here's a problem where we change A. Let's say we have, we're in an area where the field is coming towards us. So there's a uniform magnetic field coming out of the board. And I have 2 metal rails, and between the rails I put a resistor, and then this is, say, lying on the table, and then I put a piece of metal on these 2 rails that's free to slide. So this is all conducting stuff. The resistor is a resistor, so it conducts, but it has some resistance. And so the field is constant. The area is facing us. So what's the direction of the area? It's this way. What's the direction of the field? It's this way. So the angle is 0 degrees, and the angle will stay 0 degrees. Well, as this slides, what I vary is the area of that loop, right? If I slide it this way, the area decreases. And if I slide it this way, the area of that rectangle loop is increasing. And so by sliding this, I will induce an EMF and I'll get current through the resistor. So let's slide it this way and use Lenz's law to predict the direction of the current through the resistor. It's either going to be up or down. And so you've got a 50-50 chance of getting it right, so you might get it right for the wrong reason. So I can't just ask you if it's up or down because you might get it right for the, so I'll have to ask you, is it up or down, and what's your reason? And I want your reason to be use Lenz's law. Okay, so I'm sliding this way. Go ahead, try it. Sliding this way. What's the direction of the current? You look really unhappy.
Well, I was trying to make sure I
So,
didn't hear
so
what
if
I
I
was
go
actually
this way, what's
saying,
happening
so-
to the flux? What's happening to the flux when I slide this way? It's decreasing, right? You got 4 flux lines and now you have 2. So the flux is decreasing. So you want to keep 4. You want to maintain the original. Or you want to oppose the decrease.
What are you sliding?
I'm sliding this is all metal.
Yeah.
This is and this is slide. This is like 2 rails that are nailed down. This is a wire with a resistor connecting them, and then I have a metal bar that slides on the rails. Okay? So as I slide it this way, the flux is decreasing.
Are flux lines the same as field lines in this case?
Flux lines are field lines.
Okay.
But the flux is the number of field lines, right? If the number's high, the flux is high. If the number's low. So we did that by counting field lines. That's why I say it's decreasing. Because I went from 4 field lines to 2 field lines, so it decreased. So the current wants to replace the loss. So the current's gonna go in a way to give me these back, to keep it at 4. So the current, this is right-hand rule number 3 again, the current has to be this way. So it's gonna go up. What's that?
Those wires.
These are metal rails.
I'm talking about the dots.
No, what are the dots? The magnetic field line's coming at you. So this is the B. And so you're seeing the field lines, and this isn't through the loop. So those are field lines, but that's not part of the flux. If we were to say, okay, what's the flux now? It's 4, 3, 2, 1. It's going down. And so you're going to try and so the current goes up this as I slide this way, right? If I slide the other way, if you get this right, you can just reverse it, right? And how does that work? Supposing I start here, and I go from 2 to 3, it doesn't want to let it, it's going to oppose that change of 2 to 3. So now it wants to cancel that. So it wants to create a field line opposite. And so the current will be opposite. If I slide this way, the current will go down, around like that. Okay, so let's go back to this way. We have the current this way. So notice, how is the current through the bar then? Going in this direction, the current through the bar is
increasing.
It's got to be down. I'm going this way now. When I go this way, the current's up through the resistor, so it's going to be down through the bar.
Oh, you know. Okay.
Yeah, I said the bar.
Yeah.
So it's going to be down as I slide this way. This is the V. The V is the velocity, so it's sliding this way. Current will be down. Why? Because the current has to be this way. Why? Because the flux is decreasing and it's going to try and prevent the decrease. So the current's down. So this is current in a magnetic field. Here's a current carrying bar in a magnetic field. current in the field, oh, is it, the current's this way? The field is that way, what's the angle?
90.
90 degrees, so there's going to be a force. What's the direction of the force? Which right hand?
Number 1.
Number 1. So L the I, the L, the B
Is it negative
Fingers.
or positive?
Depends. What else do you see?
is what, negative or positive? No, it's a current.
I don't know.
So when it's a current, when it's a charge, you have to ask. When it's a current, it's positive. That's by definition. So
Negative J hat.
I, D, F. So down, I gotta do this. This is out of the board. So the force is this way. So as I slide the bar, there's a force this way. So what does that mean?
Negative
What's that?
I. Negative I hat. No.
It's negative I hat, but what does it mean physically as I'm sliding the bar?
Being repelled. It's being repelled.
Yeah, it's something's pushing. I feel something pushing against me. So I can't just tap the bar on a frictionless surface and let it slide all by itself. I have to do work. And there'll be a problem where, so this is toward the latter part of the assignment. So as I slide it at a velocity v, how much current do I get and how much power do I get? So watch this. So the EMF is going to be, we're not going to worry about the minus sign. dBA cosine theta dt. And the end for this is 1. Just one loop, right? It's just this rails. So the end is 1. And the B is constant. And the cosine of theta is 1. Because the area is this way and the field is this way. I'm getting maximum flux, so that's 1. And so I have B, because the n and the cosine are 1, B d dA dt BA cosine theta. And what's the A? The area of the coil. And so what is this? We'll call this L. And we'll call this the width, W. So it's D of the area, L, W, and the L is constant. Right? This doesn't change. What changes is the width. So I can take the L out. And then I have d, the d width dt. And what's the d width dt? Change in width
Right.
over the change in time. It's something very familiar. Change in width over the change in time. Good.
Exact.
Good for you. It's velocity. that equation's on your equation sheet. So you don't have to derive this. But this situation, the EMF is going to be BLD. So what's the current then through the resistor? It's going to be the voltage divided by the resistance. And what's the voltage? There's the E and the V, right? Same thing. So it's going to be the current for this situation will be BLD divided by the resistance. That gives you the current you're going to get. And so what's the power output? As I slide this at a velocity v, how much power am I going to be producing? Electric power, it's the V times the I. So if I can derive the general equation, the I is B LV over R, and the V, the voltage of the EMF, is BLV, so it's B squared L squared over V squared over R. So that's the power I produce. And what's the work that I do? There is a problem where you're going to do this, so watch. The power input, the power that I do, is the work that I do divided by the time it takes to do it. And so the work that I do is the force times the distance, or the displacement, and there. The force is in this direction, the thing's moving in this direction, so it's just the force times the distance. Cosine of theta will be 1 divided by the time. But the distance divided by the time, the distance I cover divided by the time is the velocity. So the equation for the power, the mechanical power input, is the force times the velocity. These are all numbers that are given, right? You're given the field strength, you're given the velocity at which you push it, and from that, and you have to be given the length. And from that, you can calculate the electric power output and the power input. This is the mechanical power that I'm pushing the bar, and that's what I get out. And the force that I have to push at is ILB. So this power is ILB times the velocity. Oh, well, what's the I? The I is that. So let's replace the I with BLV over R. Oh, BLV times BLV over R, get the same equation. When you do all that, are we surprised? I don't know what the heck you're talking about. You lost me 20 minutes ago.
That's why we take good notes.